Hello, this is the introduction to the AGU poster, Characteristics of Earthquake Cycles, a Cross-Dimensional Analysis. This poster is written by me, Casper, and Ilona. So our project is working on the numerical models for earthquake cycles, and there's always a common concern that large numerical models in 3D, in fluid dynamics, although they are very good, they are numerically accurate, but they are too time and memory consuming in the meaning of computation. So also it might not be optimal if the aspects of lateral depth variations with the results are not needed for the research purpose. So that inspired us to do a systematic investigate of the differences and the similarities between the model results we have for different dimensions and between the quasi-dynamic results and the fully dynamic results. And by doing this, we hope to answer the question that in what cases, what model complexity, what dimensions are needed for the research purpose. And this can also help to guide the model design and also to guide the result interpretation for future studies. So our work is about the earthquake cycle. Earthquake cycle is a repetitive behavior of seismic loading and release. So you have different phases, like the interseismic phase, nucleation phase, co-seismic phase, and the post-seismic phase. And between these phases, we have large variation of slip rate, of stress, and of the state variables in the rate and state friction, and this need to be accurately solved. So we have this code package, Garnet, to help us to do this. This is a C++ code package with the staggered grade finite difference method, and it is designed to help us to solve the multiphysics problems in the geoscience, and it can handle the nonlinear problems from 0D to 3D with a very good parallel computing solver. And the library is developed to help us to take the STM model to the next level to 3 dimensions and to include the Newton solver. And by using this code package, we can solve the multiphysics, such as the solid fluid gas coupling, the rate and state friction, and the viscoelastoplasticity rheology, and in both quasi-dynamic and fully dynamic ways. This is our model setup. This setup is guided by the SCAC sequence of Earth and aseismic slip, earthquake and aseismic slip benchmark. And we use this BP4 setup for our 3D setup and to simplify this to 2D and 1D and 0D in the end. So we have this planar vertical strike slip fault that is obeying a rate and state friction, and this vertical and is embedded in a homogeneous linear elastic half space with a free surface. And the fault has a seismogenic region with velocity weakening friction in the middle and surrounded by a velocity strengthening region. And inside this velocity weakening region, we also have a predefined high stress, high velocity nucleation zone. So the earthquakes are assumed to nucleate here at the beginning. At the top of the bottom, there are also the constant tectonic loading imposed. And if we simplify it to 2D, that means we assume that in this strike direction, we don't have any heterogeneity. So we can do a cross-section like shown in the orange. Then we have the 2D model where the fault is 1D. And furthermore, we can also simplify this to a 1D model so that we only consider a line as shown in red. This is 1D model, so we do not consider any variation along the dip direction. And even further, if we do an integral perpendicular to the fault along this 1D model, we can simplify this to 0D. And the thing to mention is that both 1D and 0D model, we choose to model the velocity weakening region only because we cannot model the velocity weakening and velocity strengthening region at the same time. And these things are, simplifications are shown as in this table. So our results for the comparison across dimensions are this. We have the differences, we also have similarities. first we should notice that different dimension models have different loading, nucleation, and rupture behavior. So like here showing in 2D and 3D, the coseismic rupture, and you can see from the figure that the rupture time is quite different. In 2D, it takes about 10 to 15 seconds for the rupture to reach to the top boundary between the velocity weakening and velocity strengthening region. But in 3D, it takes about 20 to 25 seconds. Also, you can see from the right figure that the 1D model yields even higher slip rate comparing to the 2D model and comparing to the 3D model. And the 3D model rupture lasts longest, and 2D in the middle, and 1D the shortest. And this is a reasonable result if we consider the 1D model and 2D model in terms of 3D problem, so that the 2D model is actually you have a infinitely long velocity weakening zone along the strike. So all the points along this line will start to rupture at the same time. So there will be no energy transfer in the unbroken part. So this makes the rupture time shorter and also makes the velocity peak sharper. But although they are so different in these different phases, we also find some similarities among them. So this is related to the stress drop and the energy release. So on the left, you see this stress profile with respect to time, and you have the colors from black, blue to red, from 1D, 2D to 3D. And you can see that these different curves are quite similar. They overlap quite well in terms of stress drop. So although these different points, their stress start to increase and decrease earlier or later at different time, but their stress drop is almost the same. And also on the right, there's the shear stress as a function of slip. So the surface area below this curve is the fracture energy release. So you can see that since they overlap quite well with each other, that means the rupture energy release is also quite similar between these three models. And as an appendix, we also made a code validation because we use the newly born code package Garnet. So we use the SCAC benchmarks to validate our model first. And you can see the results comparison from other modelers also participating in this SCAC benchmark. And you can see that our results are very similar compared to theirs. And you can see the slip rate, the stress, and also the coseismic rupture propagation. And their comparison all prove that this code package Garnet is valid in handling the earthquake cycle simulation. So our conclusion is that first, we have validated this code package Garnet against other benchmarks in BP1, the 2D, and in BP4, the 3D, in both the quasi-dynamic and fully dynamic approaches. And our results indicate that some important variables, such as the stress drop or the fracture energy release, they can be modeled accurately in lower dimensional models, for example, in 1D, and these models usually run hundreds to millions of times faster comparing to the 3D models. But we also admit that the different dimensional models, they result in different loading, nucleation, and rupture behavior, and this makes the recurrence interval also inconsistent. And to look for more detail, you can read my poster and other discussions. We can have the chat. Thank you.